Hello, welcome back to Lesson 3, talking about galaxies. Lesson 1, we learn characteristics of stars. Lesson 2, we learn how stars are made. Now we're going to learn about essentially the neighborhood of stars, or groups of stars. So if you put billions of stars together, you get what we call a galaxy. And just like how the planets orbit the sun, gravity is the fundamental force that causes the stars to cluster together into galaxies. If you ever go camping or you live far away from the city, if you look up in the sky at night, you can sometimes see a band of stars that look a little thicker than the rest, or at least there's these hazy white spots. I'm not sure about if you could see all of this, but it definitely you can see parts like that. Uh, you're looking at part of our galaxy. You're looking at the part of our galaxy that is really far away, and that makes up essentially the disk of our galaxy, which is a pretty cool thing to think about. I actually did not get a chance to see this in real life until until last August when I went camping. It's the first time I ever actually got to see it. So these billions of stars can have a bunch of different shapes. One of them can be a spiral galaxy. Surprise, surprise, the spiral galaxy looks like a spiral if you view it from above. Within these galaxies, there's two kinds. There's a regular and a barred. And they have these three parts that make them. They have the central bulge, the spiral arms, and the halo. And if it's a barred one, that just means the central bulge is kind of like a bar instead of a circle. The Sun is one of the billions of stars in the Milky Way galaxy. That's the name of our galaxy, which is a regular spiral galaxy that is 90,000 plus light years in diameter. That means if you're on one end of the galaxy and you turn on a light, it will take 90,000 years for that light to reach the other side of our galaxy. That's how big the galaxy is. Here's another galaxy called M101. This is not our galaxy, but this is another galaxy out there. I think galaxies look amazing. Like, this is awesome. If you ever see a picture of the Milky Way, of our galaxy, I want to make sure you realize that it's not an actual picture. It's just what we think it looks like. Because we have never been able to send a camera outside of our galaxy to take a picture of our galaxy. Because it's so big. I want you guys to realize that we launched satellites in 1970, around that time. And those satellites barely made it out of like the sun's influence. Okay? So there's no way that we've ever sent anything that's made it this far yet. So if you ever see a picture of the Milky Way that looks something like this, you are not actually seeing a picture of our Milky Way, you're seeing what we think it looks like. And it could be based off of a lot of like information and data and stuff. It's just not an actual picture. This is like a picture of another galaxy out there. And I think that's really neat. Besides spiral galaxies, we have things called elliptical galaxies. They're oval shaped. And there's all sorts of different sizes and amounts of stars in these elliptical galaxies. We also have irregular galaxies, which means they don't look elliptical or spiral. They're irregular, that's what that kind of means. Here's an elliptical galaxy called Centaurus A. We can see it does have like a really bright center. It kind of looks like it has a bar, but then everything else out there is just kind of like a bump. Then we have this irregular galaxy called NGC 445. This does not seem to have any pattern at all. It seems to be completely random, and that's why we call these irregular. Irregular. So, a long time ago when we first started looking at stars, humans first started looking at stars, not us, but literally human history. There was a couple stars that looked really fuzzy. Eventually, once we got enough detail on our telescopes, we realized that those fuzzy stars were actually just full-on other galaxies that are really far away. The story behind this is that we pointed a telescope into a dark spot of space that we couldn't see anything. We left it there for a long time and let the telescope gather as much light as possible, and we got this picture. And almost everything in this picture is a galaxy. And so if you ever look at a dark spot in space, there's all these galaxies that are so far away that we can't really see them without specialized equipment. That's insane. That should give you a sense of how large the galaxy actually is. I'm sorry, how large the universe actually is. And if you thought that was crazy, throughout the universe, galaxies actually group together in clusters that are part of larger groupings called clusters. Why is it repeat twice? I probably should say superclusters, but regardless, galaxies are in clusters. So you have a cluster of stars is called a galaxy, and a cluster of galaxies is called just a cluster. And just like gravity causes the planets to rotate around the sun, gravity causes the sun to rotate in our galaxy, or to orbit in our galaxy, and gravity causes galaxies to group together in clusters. Our neighborhood of galaxies is called the local group. And the local group belongs to an even bigger cluster called the Virgo supercluster, which contains thousands of galaxies spread across 100 million light years. Which means if you turn on a flashlight on one end of the Virgo supercluster, it would take 100 million years for light to travel across it. The farthest galaxies we can see are about 14 billion light years away. And the fact that we can see them means that the light we are looking at is 14 billion years old, right? Because it took 14 billion years for that light to reach us. So we are on Earth. This is our solar system with all the little planets and stuff around it. Now, if we zoom out a little bit farther, we can see all the stars near us. If we zoom out even farther, we can see our Milky Way galaxy. Remember, this is just an example of what it might look like. We zoom out farther, we get the local galactic group, the Milky Way being right here, but these are all of the other galaxies near us. Zoom out even farther, we get the Virgo supercluster. Our clusters over here, but this is our supercluster. Zoom out even farther, we get groups of superclusters. So these are our neighborhood superclusters. And then we have the visible universe, which is a bunch of each one of these white dots is a supercluster. So you can see literally how big our universe is based off of this picture and how small we are. It's pretty crazy. One of the theories of how the universe started is the Big Bang Theory. One of the evidences for why people believe this is most galaxies are moving away from Earth right now. So the argument is if everything exploded from a single point at one point, everything's kind of going away from that point. So there's a big explosion. All the galaxies are moving away from each other. So that's one of the reasons why the Big Bang Theory still seems like a pretty good explanation. And the idea is the first several 100,000 years, everything was in this explosion of nothingness that made everything. All the particles were too hot to actually even exist as the particles we know. But eventually, the particles cooled down and made things like hydrogen and helium. And then through the process of stars, all of the other elements were made. Because as we've talked about last section, hydrogen and helium can combine and they can make heavier elements. So that's the thought of how we got everything else, like carbon, iron, gold, silver, all that other stuff. All of it's based off of hydrogen and helium fusion. Though scientists do not agree on how galaxies formed, one theory is that the denser areas of hydrogen and helium occurred as the universe expanded, and that gravity clumped matter together in these regions. So they think that after the formation of the universe, there was just like how we think stars form in nebulas, we think galaxies formed in really big clouds, where there's a lot of hydrogen and helium together. Now, something interesting about all this is that right now, our math doesn't necessarily make sense. Our math says that we're missing a lot of mass in the universe. We're looking out at all these pictures, we're looking at all these galaxies, we're doing the math, and we're getting cool information, but we're getting information saying we should be seeing a lot more mass. The fact that we can't see it, but we know it's there based off of the math, gives rise to the idea of something called dark matter. It's matter that does not interact with light, which means if you shine a light on it, it won't reflect it, which means you can't see it because it doesn't interact with light at all. It's weird. We're not sure what that means. We're still researching it. We're still learning. This is like brand new science. We don't really know what to do. And then there's also something else. When we continue to do the math, we also get we're missing energy in our equations. There's energy that is missing. So we say, well, if we can't see this energy either, we might as well call it dark energy because we're not sure what it's doing and where it is. So our math says that dark matter and dark energy should exist, but so far we have not found any quote-unquote direct evidence. All the math just says it's there, but we haven't found it yet, if that makes sense. And congratulations for whoever actually makes it to the end of this video. You are done. And in fact, if you make it to the end of this video, and you're watching this right now, and you draw this guy, if you draw this guy, and attach him to any of the assignments, and if I see a drawing of this guy on any of your assignments, I'll give you a little bit of extra credit. That's how you let me know that you actually watch these videos. Won't be too many of you, I know that make it all the way here. So don't tell anybody about this. You can tell them to watch the video, watch to the end, but don't tell anybody about this. And that's it.